In this video, we'll be looking at addition and scalar multiplication for vectors. Let me start by reminding you how we add two vectors. So to add two vectors, well, we have to take these vectors. Let's call them v and w. Let's say the other vector w is somewhere in the plane or in space. What we have to first do is to take that vector, let's say it's over here, and shift it parallel to itself so it lands at the same with the same initial point that v has. Okay, so first of all they have to have the same initial point, and then we can add them according to the parallelogram rule, which means that we take these vectors and shift them along one another. So we shift v along w to get to that point, and that is the endpoint, our sum. But just to check, let's shift w along v, and indeed we get to the same point. So in this way we obtain a parallelogram with sides v and w, and starting from the same initial point and going along the diagonal to end up in this point that we have obtained, we get the vector v plus w. Okay, and from the construction it should be clear that it's the same thing as w plus v. So vector addition is commutative. It doesn't depend on the order in which you add them. Okay, so for another type of operation on vectors, we can look at scalar multiplication. So this was addition. Now scalar multiplication, what does it mean? Well, it means that we take a scalar, a number. So by scalar quantities, remember I've given you the example of the mass of a body or the temperature of some point in space. So by scalar we mean numbers. So we take a scalar, let's call it s. It's a real number, and we want to multiply by this real number a given vector. So let's say here is my vector v. Now this is my vector v, and when I multiply it by the scalar s, it's going to result in a vector that is along this line specified by v, and depending on the sign and the value of s, it might stretch our vector, make it longer, it might shrink our vector, make it shorter, or it could flip the vector over this point to the other side to point in the opposite direction. So let me give you examples. So for example, if I want to take this vector and multiply it by 3, it would stretch the vector to be 3 times as long. So it would point in the same direction, but it would be 3 times as long. Okay? On the other hand, if I would multiply it by a half, that would stretch the vector. It would still point in the same direction, but it would be not stretched but shrunken. So it would be a shorter version of v, exactly half as long. Finally, if let's say I would multiply it by -2, this vector v, then it would be flipped over to point in the opposite direction, and it would be twice as long. Okay, so this would be -2 times v. So just to summarize what I have said, multiplying a vector by a scalar s results in a vector that points along the line of our original vector, and here I have to introduce a new notation. For the length of a vector v. The length of a vector v is denoted by taking v and putting it in between some double absolute values. So this is called the length of, this is the symbol used to denote the length of a vector. And what is true for s times v, so we multiply the vector by the scalar, the length of this new vector, as you have seen, is going to be the length of the original vector multiplied by the absolute value of s. Okay? So the length will be multiplied by the absolute value of s, and the direction of s times v depends on the sign of v. The direction of s times v depends on the sign of s. So s could be positive, in which case they point in the same direction, or s could be negative, in which case they point in the opposite direction. Of course, you could take s to be 0, in which case you get a vector, so 0 times v is a vector of length 0. Okay, that's the 0 vector. Now let me test your understanding by giving you a few examples. So examples. Whether you have understood what we mean by adding two vectors. So let's take two vectors. Let's say this is w and this is v. And what I'd like you to do is to give me, pick the sum of v plus w. So which of the following vectors is v plus w? Is it perhaps a vector that looks something like this? Let's call this vector A. Is it perhaps a vector that goes something like this, vector B? Or is it perhaps a vector pointing in this way with the length that I've drawn? So pause the video and select your answer below. Okay, I hope you paused it and have selected option A, because if you look at this vector and shift it parallel to itself, so it ends up in here someplace. Okay, hopefully my drawing is not terribly awful, and you will see that indeed there is our parallelogram. Okay, so it's vector A. That is the sum of v and w. Now for the next example, I would like us to look at the following vector. That this vector, so this was our first example, and now it's a different example. This vector shall be vector v now, and I would like you to decide which of the following vectors is minus v. Okay, so what I did, I took v and I multiplied it by the scalar -1. So is it this vector, vector A, or is it perhaps this angle, vector B, or perhaps it's this angle, vector C? Pause the video and select the correct answer below. Okay, I hope you paused it and have selected option B, vector B, which is indeed of the same length as vector V, but it points in the opposite direction. Okay, so this is vector B. Okay, so let's move on now to giving vectors coordinates. So let's introduce coordinates. The way we do it is, so we want to look at position vectors, and we'll use the Cartesian coordinate system. So this is going to represent a coordinate system in 3D space. So here we have the three axes of x, y, and z. And I want to specify a point in space. Let's say here is that point, P, in space, using vectors. So what do I do? Well, I have this special point, the origin, in the intersection of the axes, and I have the vector going from O to P, that is the OP vector. And now, in order to obtain the coordinates of this point or this vector, we have to first project our point down to the xy plane. So we drop the endpoint down to the xy plane, and then we project this point further down to the axis. And this way we obtain the coordinates, which we'll call P1, P2. Finally, to get the third coordinate, we have to connect the point, drop the point onto the real, onto the z-axis to get the third coordinate, P3. Okay, so in this way we can express our vector OP using numbers, namely three numbers. So OP is now given by three numbers, P1, P2, and P3. Now what we can also do is we can introduce vectors of unit length along each coordinate axis, x, y, and z. We'll denote these vectors of unit length by I hat, j hat, and k hat. So these three vectors are of unit length, and they point in the positive direction along each of these coordinate axes. So if I do that, then by vector addition and scalar multiplication, I can express OP as P1 times I hat, then P2 times j hat, and add to that P3 times k hat. So what we do is we walk P1 units, we take P1 times the I vector, I hat, then add to that P2 times the j hat vector, and add to that P3 times the k hat vector. And this is how we get to our point P. Now I should say that these vectors, I hat, j hat, and k hat, are called unit vectors because they are of unit length, and they form a basis of our 3D space. Now, one more thing I would like us to have is a formula expressing the length of our vector OP using its coordinates P1, P2, and P3. So how could we express the length of our vector OP using its coordinates? Well, for this we'll need the Pythagorean theorem. So in order to have a formula for the length of our vector, we will have to find a few right-angled triangles. And just to help you with this, well, here is one. that's a right angle, although it's a bit distorted because of the perspective I'm using. This right angle here has legs P1 and P2. So the third side, the hypotenuse, that one over there, is the square root of P1 squared plus P2 squared. Okay? So in order to get the length of our vector, what we need now is to have another right angle triangle which has this segment OP in it as a side, and indeed this right angle triangle right here is such a triangle. So going from the origin to this projected point to up to P gives us a right angle triangle with sides with legs of this length, square root of P1 squared plus P2 squared, and the other leg is of length P3. So what we'll get for our formula for the length of the vector is, now we have to take the square root of this expression squared plus P3 squared, which is exactly the following: P1 squared plus P2 squared. This is what we get when we square this expression, and we had to add to this P3 squared and take the square root. Okay, so we have obtained a nice formula for the length of a position vector using its coordinates is the sum of the squares of its coordinates under the square root. Right, and all we had to do is to use Pythagoras' theorem. Okay, I hope you enjoyed this video, and I'll see you in the next one.